Hey guys, welcome to the Espressif Developer Conference 2022. Myself, Mahavir Jain, I'm working as a senior software manager with Espressif Systems. The today's talk is Espressif Privilege Separation, and this is completely open source framework which is available on the GitHub repository, and it was released sometimes back. The purpose of this particular framework is to achieve user kernel separation on Espressif platform. So let's begin. So let's quickly go through the today's agenda. I will briefly introduce this particular framework, the reasoning behind design of this particular framework, and how we went about it. What are the benefits of this particular framework? And then we shall deep dive into the technical details. And we have lined up some of the interesting demos that are built on top of this framework. So let's start with the introduction. So let me cover the background first. The typical real-time embedded systems have the monolithic firmware. In case you have worked with any MCU class devices, or for that matter, ESP IDF, which is Espressif's official IoT development framework, then it also takes the similar approach of the monolithic firmware. There is single executable or single binary that runs on the MCU. It is completely statically linked. This particular framework runs in the highest privilege mode, and it has pretty much complete system access. Now, there are certain peripherals like memory protection unit, which have been enabled in the ESP IDF, which is our IoT development framework, that can limit the access to certain memory regions. For example, only read and execute permissions for the instruction memory and no write permissions. So there is certain level of access that we can control, but otherwise this monolithic firmware has pretty much entire system access. So with this, we can see we are taking ESP32C3 as an example here, which is the exclusively supported SoC in this particular framework. And we can see the architecture over here, which is monolithic firmware executing on the ESP32C3 silicon. So what are the typical problems with traditional or this monolithic firmware based approach? A simple user application fault can take down entire system. There are also some security concerns, because if there are any remote exploits available in the firmware, then it can have a very wider attack surface, because the firmware runs in the highest privilege mode and it has access to the entire system. And the third aspect here is the firmware responsibility. In this particular aspect, the product owner or the product developer has the responsibility to manage Wi-Fi driver, the networking stack, the operating system, TLS stack, and so on. So he needs to know about all of these pieces and has to take the entire responsibility of this particular framework or the firmware. So let's start with the goal. What are we aiming here in the Espressif Privilege Separation framework or offering? So this is the traditional approach of the monolithic firmware. It executes a single firmware binary. And with this particular framework, we shall be splitting up this firmware into two separate executables, kernel.bin and the user.bin. So here we can see a secure application and a non-secure application. They shall have different privilege levels, and they shall have a different memory and peripheral access and controls. We shall go into more details in the subsequent slides. So what are the possible approaches to achieve this particular separation? Primarily, there are two ways. The first is the trusted execution environment. In this particular approach, the OS or the kernel itself is not trusted. The secure application is extremely thin. For example, we can take a use case of a firmware interacting with some crypto coprocessor over a peripheral interface. It could be I2C. Now, in this case, only the device driver that is interacting with this particular crypto co-auth processor is trusted, and rest of the operating system, networking stack, and so on is not trusted. This kind of approach helps in certain security certification to meet criteria for certain security certifications. The second approach is user kernel like separation, which we see in the general purpose operating systems too. In this, the operating system or the kernel is trusted. However, the non-privileged application is extremely thin, and it could be the product specific logic. For example, a smart connected bulb switch outlet, and it could be extremely thin or minimal firmware. This particular framework, ESP Privilege Separation, explores the second approach, which is user kernel like separation. So with the background covered, let me introduce the user kernel separation here. As highlighted, we can see the monolithic firmware approach, which contains FreeRTOS Wi-Fi driver networking stack and the application logic, all combined into a single firmware entity. And we can see the split firmware approach, where the secure application contains the kernel, FreeRTOS Wi-Fi driver, and networking stack pieces, and the user app contains the product-specific business logic. So with secure split, we are saying that both firmware images will run in the separate privilege levels. There would be controlled access to memory and peripherals. Again, this particular access is configurable and can be defined at the product definition stage. And there would be a secure communication channel between the two separate firmwares here to avail some of the services that are exposed by the secure application. For example, it could be some OS services, networking services, and so on. So let's quickly go through some of the benefits of this particular approach. So first and foremost benefit here is the separation of concerns. What we can say here is that the application specific logic could be owned by the ODM OEM. It could be very minimal firmware. For example, a firmware that is responsible for smart switch or smart outlet. And the rest of the firmware could be owned by the platform entity. Now, this firmware could contain kernel, FreeRTOS, Wi-Fi driver, networking stack, and bulk of other pieces that are responsible to run the product. Now, this particular framework also provides a secure development cycle because the non-secure entity or the application here runs in the lower privilege mode. It has a restricted access to memory and peripherals. Thus, any remote exploits or any bugs in this particular firmware have very limited attack surface because of the strict enforcements made on the memory and peripherals. The third important advantage is certification. If there is any modification in the user application part here, then we may need not go through the entire certification process, which is required for some of the frameworks or the products. So it would help in certain scenarios and where the protected application is not being modified. And the fourth important advantage here is the better exception handling or the better exception management. Since this non-secure application does not have the entire memory or the peripheral access, we could easily handle their exceptions in a well manner. So we will have more details on this in the subsequent slides and the technical details too. Let me introduce the ESP Privilege Separation framework. And what it helps to achieve is the separation of firmwares. It provides a system call interface for the two firmwares to interact with each other. There is a configurable memory and peripheral access, and this could be set during the compile time or the build time options itself. There is flexible memory split for the protected and user application. And the biggest advantage is it also provides a consistency with ESP IDF APIs. So we have envisioned that moving ESP IDF examples into this particular framework should be very convenient and easy. So here is the traditional approach that we discussed, which is the monolithic firmware based on ESP IDF framework, and it's a single executable. And with the ESP privilege separation, one could achieve a split in the firmware into two separate entities, protected application and the user application. Protected application runs at the highest privilege, and the user application has restricted memory and peripheral access. And there is a secure communication channel between these two entities in the form of a system call. So with this introduction, Now we will move into the technical details section. So I will hand over to my colleague Sachin Parekh, who is working as a senior software engineer with Espressif Systems. Over to you, Sachin.
Thanks, Mahavir, for introducing and providing a brief overview of this framework. Now let's talk about the technical details. Let's begin by looking at how a project in this particular framework would be structured. So on the left, we have the Blink project in the typical IDF scenario. It has a top level CMake list, which includes all the routines required to build the application. Then there's partition.csv file, which defines the flash layout. And then we have the main folder. The main folder consists of the app_main source file, where the actual code is being written. So this is where the application logic exists. And once you build this project, it would generate a blink.bin file, which would be your application, the monolith application. Now let's see how this same Blink project is structured in the ESP Privilege Separation. So it has a similar top level CMake list, the partition.csv file, and it has two different application folders, protected app and user app. Now the protected app consists of its own main folder where the protected application resides. So whatever code that is being written in the main folder would be built as the protected application. And then the user application also has its own main folder, and the code written inside this main folder would be built as user application. So now one thing I would like to highlight over here is that the privilege separation framework is built on top of IDF. So we have tried to maintain the same workflow as you are already familiar with. So the Blink project inside the ESP privilege separation would build two different application, protected app and user app. And if you're familiar with the CMake build system, then the user app is built as a external project. And the project uses the same IDF build commands. So idf.py build would build the entire project, and it would build two applications, the protected app and the user app. idf.py flash would flash these binaries onto the device. So once these binaries are flashed on the device, let's see how they boot up. So here on the top, we have the application boot up of a typical IDF application. So on reset, the ROM bootloader starts executing. The ROM bootloader looks for a valid second stage bootloader in the flash, and if found, it loads into the memory and hands over the control. The second stage bootloader is responsible for initializing the system. And once initialized, the second stage bootloader looks for a valid application in the flash, and if found, it loads into the memory and hands over the control. Now, at the bottom, you can see the application boot up flow of a privilege separation project. So the first two stages are the same. That is, on reset, the ROM bootloader starts executing. It then loads the second stage bootloader, and the second stage bootloader loads the protected application from flash. Now, typically, the protected application would consist of the FreeRTOS kernel. And once the entire OS is up and running, it would then look for a valid user application in the flash. And if found, it would set appropriate permissions and execute the user application in a separate task. So in this way, we have both the protected application as well as the user application running concurrently on the same device. Now, if they are running concurrently, we need to make sure that their boundaries and their access permissions are managed. So for that, we need something called as execution environment. The primary function of the execution environment is to provide two things. First is a component that manages the permission, and the other is to provide a component that manages the privilege level. So in ESP32C3, we introduced two new hardware peripherals called permission control, which, as the name suggests, is responsible for managing the permission, and the other is the world controller, which is responsible for managing the privilege level. So in ESP32C3, there are only two worlds that are being supported currently. One being world 0, which will also refer to as secure world, and world 1, which will also refer to as non-secure world. Now, these two worlds would have their own set of permission controls. So the permissions of a particular region can be configured depending on the world that is being executed. So now let's talk more about the permission control peripheral and its function. So the permission control is responsible for splitting the memory between user and the protected or the kernel memory. So it's responsible for enforcing strict permissions. So if there is any violation, it needs to be caught at real time. And if in case there is a violation, it also needs to log certain information, which will help us debug the problem. So now let's see how the internal RAM is being split. So here you can see the diagram of the entire SRAM block. So the permission control has a concept of split lines. So there are three different categories of split line. The first is the main ID split line, which is responsible for splitting the RAM into IRAM and DRAM. So this is the main ID split line. The other category is the IRAM split line. It is responsible for splitting the IRAM block into further blocks. And similarly, we have the DRAM split line, which is again responsible for splitting the DRAM into different blocks. So now once we have split the blocks in multiple regions, we can also configure them. And we'll configure them in such a way that the non-secure world, or the world one, can only access the topmost IRAM block or the bottommost DRAM block. And hence the labels user IRAM and user DRAM. Now, if the non-secure world tries to access any region in the protected space, then it will raise an interrupt. Now, one thing to note over here is that these lines are highly configurable and they can be moved up and down depending on the use case of the application. And other thing is that the reason why we have chosen this particular layout of user IRAM followed by protected IRAM followed by protected DRAM followed by user DRAM is because it allows us flexibility when updating the protected application. So if in case the future protected application requires more IRAM or more DRAM, then we can simply move the main ID split line up and down to accommodate these changes without affecting the user application. So similarly, we have also split the flash cache. So we are talking about the flash virtual memory address space and not the physical flash. So we have split the flash right in the middle. So the top 4 MB belongs to the protected space and the bottom 4 MB belongs to the user space. So now we have the permission in place. Now let's see how the privilege are switched. So the reason why we need a mechanism to switch privilege is because the protected application as well as the user application are running concurrently on the device. So let's first look at how the switch from secure to non-secure world happens. So for that, we need to configure the registers of the world controller. So the world controller consists of a dedicated register, which needs to be configured with the address of an instruction. And once the CPU fetches that instruction, it would switch to the non-secure world. So for example, if you want to execute function foo in the non-secure world, then you need to configure the world controller register with the address of foo. And now whenever CPU would execute function foo, the world will automatically switch. So you need to know the instruction at which the world switch would happen, and you need to configure the world registers every time you want the switch to happen. So now let's talk about how to switch from the non-secure to the secure world. So this can only happen through interrupts and exceptions. So any interrupt or exception generated on the device would automatically switch the world from non-secure to secure world, and then the corresponding handlers would always execute in the secure world. So there are certain architecture specific instructions, for example, eCall in RISC-V, which allows us to generate a synchronous exception so that we can deterministically switch from non-secure to secure world. So let's see how permission control and world controller work together to enforce permission. So let's say we have the following configuration done for the following address range as highlighted over here. So as you can see, world 0 has complete access, read, write, execute access to any address in this range, while world 1 only has read access to this range. So now if world 1 tries to perform a write operation on any address in this space, then it would trigger a violation interrupt, while world 0 wouldn't trigger any violation interrupts. So now let's see how we can handle the exception in the user space. So in the monolithic application, if there is an exception or hard fault that occurs, then there is no guarantee of the state of the system at that point. So naturally, we just reboot the entire system. But in this particular framework, since we have the protected app and the user app isolated and with well-defined boundaries, we can be sure that when the user application crashes or an exception happens in the user application, then it won't impact or it won't affect the protected space state or the protected app memory. So because of that, we can ensure that the protected application can continue to run even while the user app has crashed. And this can allow a lot of different functionalities. One such that I can think of is the protected application can collect diagnostic information of the crashed user app. And if there is a connectivity, then it can report it back to the backend in real time. So now let's see this in action. So now here we have the blink example, and I have tweaked it in a way that it would generate an exception when a button on the board is pressed. So I have already built the application, so I won't be building it again, but you can just build it through idf.py build, and it would just build it. And I have also flashed it on the device so that we can save some time. So I'll just run idf.py monitor, and you can see that this is the device that I'm working upon. And you can see that the LED is functional and it is blinking at a regular interval. And if you look at the logs, you can see that the bootup flow, the bootup sequence that we have discussed, that the ROM bootloader executes, and then the second state bootloader executes, and then this is where the protected application is booted up. And then once the protected application starts the scheduler, it then looks for a valid user application, and if found, it loads into the memory and then starts executing it. Now the protected application as well as the user application are running concurrently. So this print that you see, hello from protected environment, is actually from the protected application, while these prints that you see are from the user application. Now if I have this button over here, which can be used as an input, and once I press this button, it will lead to a crash. So if I press it, you can see that a crash dump has been uh, observed. So what happens is, the user application has crashed because of some reason, and then once that happens, the protected application detects it, and then it dumps a bunch of information on the console. So you can see it has dumped why exactly the error occurred, and in which particular task did the error occur, and then it also dumps the CPU state at the time of exception. So a lot of information can be inferred just by looking at the state of the CPU during that time. And now if you have the elf file of the user application on your system, then the idf.py script can also generate a backtrace for you, and this is exactly what it has done. So you can see it has generated the backtrace, and it is pinpointing to this particular application, and in this file, and on line number 49. So if you look at the statement, it says that I'm trying to store value 0 at null pointer, right? So this definitely is a problematic statement. So just by looking at this dump, I was quickly able to realize my mistake. And if you have the connectivity on the device, then like I said, the protected application can gather all this information and can send it back to the backend in real time. You can see that the blink is still functional, the LED is still functional, and you can still see the prints from the protected environment. So this is one of the exciting features that of this particular framework. So now let's get back to the details, technical details. So we saw an interesting demo of the user space exception handling. Now let's go further into the technical details. Now there can be a requirement where the user application wants to access certain protected services. For example, the certain OS primitives. So the user code wants to spawn a new task, or let's say wants to grab a semaphore. So for that, there needs to be a way in which the user application can access those services. Now, if it directly tries to execute those routines, then uh, it would lead to a violation interrupt, as we saw earlier in the demo. So there needs to be a proper interface through which it can be done. So in this, we have implemented the system call interface, through which the user code can request certain services, and if they are valid, then the protected application would execute uh, those in the higher privilege levels. So what exactly goes into the system call is that the user code uses certain architecture specific instruction. So earlier I mentioned the ecall instruction in RISC-V. So what this user application does is it populates the CPU registers with its request, and then it calls the ecall instruction. As soon as the ecall instruction is encountered by the CPU, it generates an exception. The exception causes the world to switch to a secure world, and the secure world handler pitches in. Now, the system call handler would validate the user arguments, and if they are valid, then it would execute the intended functionality. So there are certain requirements of this system call interface, that one, it should access protected services in a controlled manner to the user application. Second, to ensure that no user argument is passed to the actual functionality without validation. So if there's a null pointer, you need to make sure that the null pointer is not passed as it is. The checks should be in place. And then other thing is to ensure that no data is being leaked back to the user code once it returns back. And it is also the responsibility of the system call interface to ensure that it returns back to the same place where the user code requested the system call. So you would be wondering if if you are required to implement all the system calls. Well, that's not the case, because the framework has most of the core services system calls provided. So we have provided system calls for the OS, the networking stack, the Wi-Fi drivers, and so on and so forth. But still, there could be cases where you would want to implement your own custom system calls, right? So for that, we have made this framework extensible in a way that you can define your own custom system calls at a project level. So you don't need to even tinker with the framework. You can just define your own custom system calls at the project level, and the entire build system would take care of it. Then there's also the ability of API consistency. So what I mean by the API consistency is that you can use the same function prototype in the protected application as well as user application. So let's say, for example, xtask create or vtask delay. So these are certain OS primitives which will be used by both protected application and user application. So now if protected application uses vtask delay, then the build system would pick the vtask delay implementation from the free RTOS. But now if the user application calls vtask delay, then the build system would pick the system call implementation which we have provided in the framework, and it would be routed through the system call interface. So this API consistency is achieved through the linker flags. Now let's look at how the components of the IDF are split in this application. So the component split is pretty flexible. Let's take an example of the ESP HTTP client application. So here we have the entire TLS stack, and it is up to the developers of the protected application to decide where to place the ESP HTTP client component. So one example would be to place the entire TLS or the ESP HTTP client component inside the kernel. So for that, protected application would have to implement its own custom system calls for the ESP HTTP client component, and then the user application would use this system calls to access HTTP client or the network. Now, other approach is to only handle the lower level socket operations at the protected app level and defer the rest in the user application. So for example, here the entire TLS stack can go into the user application, and the protected application would just care about the socket operations. So this is the real life example which I was just talking about. So we have this ESP HTTP client example in our repository, which you can go and try it out. So in this, what we have done is the user app has the entire embed TLS stack and ESP HTTP client component, and the protected application only handles the operating systems, the Wi-Fi stack, and the networking stack. So in this way, the component splits can be achieved the way you want and depending upon the application use case. So now let's look at certain design choices that we have made. So the first is the device driver model. So in the IDF application, if you see, the device drivers are not consistent. Each and every peripheral has its own set of APIs and they have different prototypes. So what we have designed, or what we have envisioned, is that the user application should not deal with all those different APIs. So we have planned to implement the entire device driver in the protected space and expose these device drivers to the user through the POSIX compliant IO system calls, which are open, read, write, etc. So from the user app development side, you just need to worry about these 4 or 5 function calls, POSIX compliant function calls, and it will give you access to various peripherals. And the other approach is to grant the user application access to the peripheral register address, and then it would be the responsibility of the user application to develop its own driver. Now, naturally, the follow-up question is, how would the user space interrupt or event handler handle? So now the user code cannot be allowed to execute in the ISR context. The reasons is that it could lead to a nasty misbehavior. So for that, we had to implement our own dispatching mechanism in which we create a different task and dedicated task, which executes the interrupt or the event handler of the user as soon as the event occurs. So these handlers run in the task context, but they are ensure that they get the priority over all the other tasks. Now, this definitely has certain impact on the memory, and it also introduces certain latency. So now let's look at the OTA part. So now, since we have the protected application and the user application running independently, one natural requirement would be to know whether the user application can be updated. And yes, we do provide this facility. So it is possible to update the protected application as well as user application in this framework. Now, since the update of the application relies on verifying the image and writing on the flash, this entire workflow is only handled by the protected application. Now, it is also possible to independently update protected and user app at different time intervals. So it can be possible that you first update the protected application and then at some later stage you update the user application. Now, security is also of a concern while doing OTA upgrade. So we also have the ability to securely sign and verify these application while doing the OTA upgrades. So it ensures that only authorized code can execute on your device, and both of these applications can have different signing keys, so it decouples them from one another. So now let's look at the overall OTA upgrade workflow. So like I mentioned that the entire process is handled by the protected application, but it's the user code which will instigate. So initially it would just pass the URL to the protected application through system call. And this URL should consist of a valid user application. It verifies the URL, and then once it's verified, it handles the entire OTA workflow in the background. Now, if you look at the partition table, you would see that we maintain two symmetric app partitions, one for protected application and one for user application. So over here, OTA underscore 0 and OTA underscore 1 are corresponding to the protected application, while user 0 and user 1 correspond to the user application. So now let's take a look at the demo and let's see it in action. So here we have the ESP user OTA example. It will demonstrate the update of the user app through Wi-Fi. So here you can see that I'm running a local Python HTTP server where I have hosted my binary, which I'll be updating. So again, I'll just make sure that I'll just flash. So in this particular application, the protected application connects to the Wi-Fi, and the user application does nothing at this particular moment. And now once we update the user application, it should start blinking the LED, which we have already seen in the previous example. So I'll be updating the user app with the blink example. So if you can see over here, it just has the LED at the solid state, and it's solidly on it, and it doesn't toggle at a regular interval. So now what I would do is I would just copy the command to update. So here I'm passing the URL through CLI. So as you can see, I can input something. So the command is user OTA followed by the URL. So I'm passing user OTA followed by the URL. And once I hit enter, the OTA workflow would begin. Now you can see over here, as soon as I have updated, you could see that the LED has started blinking. And if you look at the logs, you would realize that the update was only roughly around 100 KB. So this is one of the feature of this framework where the user application is very minimal. So here only around 100 KB was required to change the identity of this device or change the user application, as opposed to the typical 1.5 MB of the entire application. Now let's get back to the technical details. So with all the features and highlights being talked about, let's see what impact does this framework have on your application. So definitely there are impacts in the performance and the resource areas. So every system call execution has an overhead of certain CPU cycles, and then since the user application code can never execute in the ISR context, it has certain latency while servicing the interrupt routines. So the numbers are highlighted in these slides. And there's also certain resource impact. So each user space task requires a corresponding kernel stack. This is because the kernel stack ensures that the data isn't being tampered while executing the system call, and no data is also leaked out. And there are certain tasks which are required to dispatch the event or the ISR handlers and to clean up the user memory. So even these tasks consume certain memory. So with all that discussed and talked about, let's see the resources that are available online for you guys to try it out. So we have the repository hosted on the GitHub, and then we also have our documentation where you can find all these details that we have talked about and much more in greater depth. We have also published 2 blog post articles, one being the introducing ESP privilege separation and the other being a case study, a real world case study where we are using ESP Rainmaker and ESP privilege separation framework together. And if you want to dive deeper into the chip, you can refer to the technical manual reference and you can find a lot of information over there. One thing that I would like to note over here is that the framework is still in the beta phase, and we urge you to try this framework out at your end, tinker with it, and we'd love to hear your feedback and the use case that you are envisioning. And in the meantime, if you encounter any bugs or issue, feel free to report in the same GitHub repository and we'll be happy to help. With that, I would like to conclude this presentation. Thank you for watching this presentation and we'd like to hear back from you. Thank you.